Hello guys, how are you today? Today I'll be talking about chapter 5 topics. Okay, this is from the topics, the notes, anything above the chapter 5 topics or that I talked previously about. It is an actual chapter from the book. The chapter 5 topics, it was very complicated. I don't think I would be able to just explain it from the notes. So that's why I preferred to make a summary. So chapter 5 talks about organic chemistry. Now, before we start, what is organic chemistry? What will we be studying or what will we be talking about? Very simply, organic chemistry, okay, it is the study or the chemistry of carbon and its compounds, except oxides, carbonates, and hydrogen carbonates. So, organic chemistry, it is the chemistry of carbon and its compounds. Okay, now carbon and its compounds, except, so keep in mind there are some exceptions, except oxides, carbonates, and hydrogen. Carbonates or bicarbonates, so carbonates or bicarbonates. So if we were to be asked what is organic chemistry, it is the chemistry of carbon and its compounds, except for oxides, carbonates, hydrogen carbonates or bicarbonates. So let us move on to the first topic talked about in the organic chemistry, which is covalent bonds. Now we're talking about covalent bonds because organic chemistry is the chemistry of carbon, and carbon, it can be a covalent compound. So what you need to know about covalent bonds is that the carbon atoms in the covalent bonds, carbon atoms, they can form very long chains. So because of these covalent bonds, the carbon atoms will be able to form very long chains, or they will be able to form rings. So because of these covalent bonds, carbon atoms will be able to form very long chains, and they will also be able to form rings. Now, something very important is that carbon atoms must form 4 covalent bonds. So a must for the carbon atoms is that they are supposed to form 4 covalent bonds. And we have different types of covalent bonds. We could have just like single bonds, so we could have carbon, something like this, and this angle over here, remember, each one of them has an angle. If we're talking about only single bonds, let me just change the representation a little bit. Let us say this is a carbon atom, okay, made up entirely of only 4 single covalent bonds. So the angle between these 2 covalent bonds would be 109.5 degrees. Keep this in mind. So the first type of covalent bonds is either 4 single covalent bonds. The second type of covalent bonds, it would be 2 single bonds and 1 double bond. So these over here are the 2 single bonds, and this over here is the double bond. And the angle made between the single bond and the double bonds is 120 degrees. Now, the third type of bond we have is that it could be a single bond and 3 bonds, meaning a triple bond. So it could be a single bond and a single triple bond, and the angle in between them is 180 degrees. And now finally the fourth and final type of bond, it is the 2 double bonds, and their angle is also 180 degrees. So about covalent bonds, we know because of covalent bonds, carbon atoms can form very long chains or even rings, but a must for carbon atoms is that they have 4 covalent bonds. Why? It is because carbon atoms have 4 free electrons or 4 valence electrons. So The first type we have is that if they are all single bonds, then the angle is 109.5 degrees. If we have two single bonds and one double bond, the angle is 120 degrees. If we have one single bond and one triple bond, the angle is 180 degrees. And then finally, if we have two double bonds, then the angle is 180 degrees. Now, since we are talking about covalent bonds, let us move on to the general topic of bonds. So there's covalent bonds by themselves, a different topic, and then bonds. Now, in organic chemistry, in what we're taking, we're going to be discussing two different types of bonds, the saturated bonds and the unsaturated bonds. And for each one, we are going to be listing some characteristics. Now, for the saturated bonds, they have only single bonds. That means no matter where you look, you are gonna see only single bonds. You will never find a double bond, a triple bond. You will never find these types of bonds. You'll find only single bonds. And these usually, they are found in the groups called alkanes. Now, alkanes, their general formula is CnH2n plus 2. We will discuss later on more about alkanes and what they are. Now, we finished saturated bonds. We will move on to unsaturated bonds. Now, unsaturated bonds, they have at least one double or triple bond. So let's say you have a million single bonds, but one of them becomes a double bond, then directly this is unsaturated. Okay, so if all of them are single bonds, it's saturated. If you have at least one double or triple bond, it is unsaturated. And usually you find these types of bonds in alkenes, and the general formula for alkenes, it is CnH2n. So we finished discussing about bonds. What we need to know is that alkanes and alkenes, they are organic molecules. So how could we possibly represent organic molecules? So the title for this page is going to be representing organic molecules. We have 5 important ways on how to represent organic molecules. We have the first way being the empirical formula, which is the simplest formula. If we are talking about alkenes, for example, this is alkenes, CnH2n, the simplest formula would be CH2, meaning you cannot simplify it any further. Or if we're talking about alkanes, for example, its simplest formula would be CH4. Okay? Now, the second way is using the molecular formula. Molecular formula could be, okay, let's say I have 2 carbons. If I have 2 carbons and I'm representing an alkene, it would be C times 2, H 2 times 2. So it would be C2H4. Or if I was representing alkanes, let's say I have 2 carbons in the alkanes, it would be C2H6. So as long as it's not an empirical formula, which is the simplest formula, then yes, for sure, this is a molecular formula. Then we have the displayed method. What is the displayed method? The displayed method is just to represent it. For example, if we are representing the alkene, C2H4, we know that alkenes are unsaturated, meaning that they have at least one single or double bond. So it would be C and C because we have 2 carbons, double bond, let us say, okay? Because this is the formula of C2H4, and you would have an H over here, an H over here, an H over here, and an H over here. However, if you are representing it for alkanes, on the other hand, you would have C, single bond C, because remember in alkanes they are saturated, and you would have 1, 2, 3, 4, 5, 6 hydrogens. All right? So this is it for the displayed. Then we have the structural formula. Now, structural formula, I believe you only use it for the acetic acid, which is vinegar. For example, it is CH3 COOH, I believe. This is the acetic acid. Usually people represent it C2H4O2. This is in the molecular formula, but in the structural formula, it is actually CH3COOH. And then the fifth and final method is the skeletal formula, which I don't believe anyone uses. This you will just put all of the elements and their bonds without the carbon and hydrogen. So these are just 5 ways to represent the organic molecules. Now, talking about representing, let us move on to the naming processes. In the naming processes, we need 2 things. We need a prefix in addition to a suffix. Now, the suffix will depend on what? Will depend on from which family it is from. So if it's an alkane, an alkene, an alkyne, an alcohol, or even an acid, this is the suffix we will be using. For the prefixes now, we have something different, something we need to memorize. We need to know that when we are using the prefixes, we are going to be counting the number of carbons. So I'm going to put here, just a bracket over here. Prefix means the number of carbons. Always keep this in mind. Okay, so let me write just their order. We have meth, eth, prop, but, pent, hex, hept, oct, non, and dec. These are 10. Okay, these are the numbers from 1 until 10. So this is if you have 1 carbon, if you have 2 carbons, if you have 3, if you have 4, if you have 5, if you have 6, 7, 8, 9, and 10 carbons. Just keep these in mind. This is for naming the organic molecules, okay? So again, to name the organic molecules, you will use the suffix from which family they are in, if they are in alkanes, alkenes, alkynes, alcohols, or acids. And for the prefix, you will use meth, eth, prop, but, pent, hex, hept, oct, non, and dec, based on the number of carbons you are given in the chemical equation. So now let us move on to the topic of hydrocarbons. Hydrocarbons are very important. These are like the whole just like general of organic chemistry. In general, hydrocarbons. What are hydrocarbons? Hydrocarbons, they are, I'm going to put a small arrow to show that this is the definition. They are an organic compound, all right, that contains only carbon and hydrogen, hence hydrogen. Hence why we have the name hydrocarbon. Hydro refers to hydrogen and carbons refers to carbon. So hydrocarbons, they are organic compounds that contains only, nothing else, only carbon and hydrogen. So an example could be an alkane or an alkene, okay? Now again, talking about hydrocarbons, we have 2 types. We have the saturated, that we know it is only the alkanes, okay? And then we have the unsaturated, unsaturated, which we know it is the alkenes, and a new addition that we have, it is the alkynes. So remember, when discussing about hydrocarbons, you have 2 types. You have saturated and unsaturated. Saturated, it's only alkanes, whereas unsaturated, it is alkenes and alkynes. Now, what is actually the meaning behind alkanes, alkenes, alkynes? What are these? These, they are called homologous series. We spell it like this, homologous series. Now, what is the definition of homologous series? It is a family. A family means anything that has similar properties. Some examples of homologous series are alkanes, okay? Alkenes, alkynes, alcohols, and acids. These are the homologous series we will be talking about. They are alkanes, alkenes, alkynes, alcohols, and acids. Now, how do we know if these are actually coming from the same homologous series? If they are from the same homologous series, so let me just write, if they are from the same homologous series, they will have 4 very important similarities. They will have the same general formula. Okay, keep this in mind. They will have similar chemical properties. They will have the same functional group, and they will have similar physical properties. Now, keep in mind, if they are from the same homologous series, they can either be same or similar. Same means it's a constant. Similar means there's little differences, but in general, they are the same. So same general formula, similar chemical properties, same functional group, and similar physical properties. Keep these in mind. Now that we're discussing about the homologous series, let us discuss about one of the most important parts, which is the alkanes. Alkanes is one of the most important and well-known homologous series. We will start with its general formula. The general formula of alkanes, as we know it to be CnH2n plus 2. We know that alkanes, they are saturated hydrocarbons, and we know that saturated means they will form only one bond. And because they are saturated hydrocarbons, because they do not have any free bonds to react, that means they are unreactive with other hydrocarbons, Okay, so far we know that alkanes, they have a general formula, CnH2n plus 2. They are saturated, meaning they only form single bonds, and because they only form single bonds, that means all of their bonds are being used, so that means they are unreactive with hydrocarbons, and they have no specific functional group. Okay, now how do we name the alkanes? This is going to be a little long and a little difficult. Now, you have 2 different types. You have the naming process, so the name process. You have 2 different types, whether it is unbranched, meaning there are no branches, or if it is branched. If it is unbranched, then very simply you're going to use a prefix depending on the number of carbons present, so prefix depending on the number of carbons present, plus "-ane", the suffix "-ane". Where did we get the suffix "-ane" from? From alkanes. Its suffix, its ending is "-ane", A-N-E. So let's take an example. Let us take C2H6, okay? So let us draw, for example, C2H6, okay? And let us try to name it. C2H6 would look like this. So you have H here, H here, H here, H here, H here, and H here. So we said the naming process, first of all, depends on what? It depends on the number of carbons. As you can see, it has 2 carbons. And if you memorized, or you can go back to the notes, we said that 2 carbons means that it is F. So the prefix is going to be F. And then very simply you will add to it ane, so it's gonna be ethane. Now this is the first name process, which is the unbranched. I don't know why I wrote unbranches, it's unbranched. Okay, now the second naming process, which is even more important, it is called the branched. Let me just zoom in and write. The branched process. First of all, what does a branched mean? Or what does a branch mean? A branch means that one bond of a carbon will extend so that another carbon will branch either on top of it or below it. We will see some examples later so that it is clear. Okay, so that it is clearer, we will see some examples. So we will have a few steps in labeling the branched alkanes, okay, or just like anything branched in general. The first thing we are gonna do is we are gonna choose the longest chain and count how many carbons there are. So we are gonna choose longest chain and count number of carbons. Okay, this is the first step. The second step, okay, it is on how to number the carbons. So, how to number carbons. How do you know which one is the first carbon, which one is the last carbon? It depends on the branch. If a terminal means the starting or ending carbon. If a terminal is closer to the branch, then this means it is what? Then this means it is the first or the starting carbon. And similarly, if a terminal is farther or like far to the branch, then it is the ending carbon. And when we are talking about branches, we have to keep in mind that branches, they are usually what? They are usually alkyls, okay? Alkyls. And the alkyls general formula, it is CnH2n plus 1. So let us take an example of the branched hydrocarbons or the branched alkanes. We will take just this example. I'm gonna draw it over here. Now this over here, as you can see, it is a branched alkane or a branched organic compound. Now how exactly are we gonna be naming this branched organic compound? First thing we are gonna do is we're gonna locate the terminals. In this case, we have 3 terminals. 1, 2, 3. As we can see clearly, this is our branch. We will call this our branch. So what we are gonna do is we're gonna take the skeleton or the base, which is this over here, which is also, by the way, the longest chain of carbons, and we are gonna count the number of carbons. Now, as you can see, we have 1, 2, 3, 4, 5, and 6 carbons. But how are we going to numerate them? Are we going to numerate them from left to right or from right to left? Very simply, we said to numerate them, we need to locate the starting carbon and the ending carbon. So we located our terminals. We have this terminal over here and this terminal over here. To locate the starting carbon, we have to see which is the branch closer to. As you can see, the branch is closer to this carbon. That means this is our starting carbon. So this is going to be number 1. And this is going to be number 2, 3, 4, 5, and 6. Now, why exactly are we naming them? Numbering them? This is all part of the naming process. So we have 6 carbons on the base, and how many carbons do we have on the branch? We have 2 carbons on the branch. Okay? So how are we gonna name this? The first thing we're gonna do is we're gonna say, okay, on which carbon is the branch located? It is located on the 3rd carbon, so you're just gonna put the number 3. Okay? Next thing we're gonna do is we're gonna see how many carbons does the branch contain, or what is the name of the branch? Okay, we know it contains 2 carbons, and we know that 2 carbons is gonna be eth, so it's gonna be eth with the terminism or the suffix YL, so that means it is ethyl. So it is 3 dash the branch name, which is ethyl. Okay, and now we are gonna take the name of the base. We said we have 6 carbons, and 6 means hex, so it's gonna be hexane. Why did we choose ane? Because it is very simply an alkane. And just like that, we named our branch, so it's gonna be 3-ethyl hexane. This is probably one of the hardest things in the organic chemistry. Everything else is much easier, only the naming is a bit more difficult. Of course, this is not the only type of branch we might meet. We might meet other types of branches. So just give me a moment to draw them. So as you can see, we have 2 different types of bonds. Very simply, what's different here is that instead of actually drawing the CH3 as, for example, it's like this CHHH, they simplified it and they directly put it as CH3. This is another way to do it. But the main purpose of this different bond is that you have 2 bonds, okay? How do we name it? We name it alphabetically. So keep in mind, when we have 2 bonds, we will name it alphabetically. Of course, important is that these 2 bonds are on different carbons, whereas here in this bond, we will have CH3 and CH3 on the same carbon, and you are gonna see how we are gonna name that. So if we are gonna list this alphabetically, first thing we need to do is we need to count the number of carbons. Let us see which carbon is closer to which one. This one is exactly in the middle. There's 2 to the left and 2 to the right, whereas this one, it is closer to this terminal than this terminal over here. That means this is 1, this is 2, this is 3, this is 4, and this is 5. Okay? This is the first step, which is very important. Now, the second step is we need to locate where the bonds are located. We have the branches are located. We have one of the branches to be located at 2 and another of the branches to be located at 3. Because they are multiple, we are not gonna proceed more than this for now. Now what we're gonna do is we are gonna name the bonds. Okay? Or sorry, name the branches. This branch over here, its name is methyl. Why? Because it has only 1 carbon. However, this branch over here, as it has 2 carbons, it's going to be ethyl. And they said we need to name it in alphabetical order. So to name it in alphabetical order, we're going to start with the ethyl because it's an E. So it's going to be 3-ethyl because we started with 3, the bond that has ethyl. Then another dash, 2-methyl. And then we're going to put the number of carbons. We have 5 carbons in the base, so it's going to be pentane. This is the way to do it when you have branching, but 2 branches on different carbons. Now, what should we do if we have two branches coming out of the same carbon? If we have same carbon, there are coming different branches. Let us see what is gonna happen. The first thing we're gonna do is we are gonna locate the locations of these carbons. So this one is exactly in the middle, so we will not focus too much on it. Whereas this one, it's closer to this terminal than this one. That means this is gonna be 1, 2, 3, 4, and 5. Okay, now the next thing we're gonna do is we're gonna focus on where the bonds are located. We have 2 bonds being located at 2, whereas only 1 bond is located at 3. Now keep in mind, because we have 2 bonds coming from the same carbon, we will need to say that we have 3 of whatever we have. So this is a methyl, this is also a methyl, and this is also a methyl. Why? Because each of them contain 1 carbon. So because each of them contain only 1 carbon, we can say that it is trimethyl, or we have 3 methyls. Okay, so the first thing we're gonna do is we're gonna list. We have 2 carbons being branched from the same carbon, so you're gonna have one at 2, another is also at 2, so you have this one is at 2 and this one is also at 2, and then you have this one to be at 3. But because they are all methyl, meaning they all have 1 carbon, we are gonna write it as trimethyl. And then finally we will count the number of carbons in the base. We have 5, so it's gonna be pentane. So very simply, it's 2, 2, 3 trimethyl pentane. Now these, I'm not sure if they will be coming, but it's better to learn them than to not it's better to be safe than sorry, that's the expression. So you have the naming process in the unbranched, and then you have the naming process in the branched. So please pay attention to these. One more thing I am gonna add is that we have something called structural isomers. What exactly are structural isomers? Structural isomers are very simply organic compounds having the same molecular formula but different structural formula. Structural isomers, they have same molecular formula but different structural formula. So let us take an example. Let us take butane. Butane, it is C4H10. If you were to draw it regularly, it would be 1, 2, 3, 4 carbons, and surrounding it you have the H's, so it would look something like this. So very simply, this is what a regular butane would look like. So the molecular formula is C4H10. What if we do something that has also a molecular formula to be C4H10? But instead of looking like that, it will look like this. It will have 1, 2, 3 carbons. 1 carbon is branched, and then you have the same number of H's. So as you can see, its structural formula is also what? Structural formula is also C4H10. But if we were to name this based on what we learned previously, if we are to name this because it's at the center, it could be either 1, 2, 3 like this or 1, 2, 3 like this. It doesn't matter because it is in the center. So this, it's gonna be 2 dash, because there's 1 carbon, it's gonna be methyl, and because you have 3 carbons in the base, it's gonna be propane. So as you can see, they have the same molecular formula, which is C4H10, but their names are different, butane and 2-methylpropane, and as you can see, their structures are also different. These are called structural isomers. One thing I wanted to keep as a notice, very, very important idea, okay, is that isomers or any branching never occurs on the terminals. So isomers or any branching never occurs on the terminals. Okay, also some other things to keep in mind is that as the number of carbons are increasing, the melting, boiling point, and densities are increasing. So there will be an increase in the melting point, in the boiling point, and in the densities. All of this is because of the number of bonds. As the number of bonds increase, they will become stronger. Okay, it will be harder to break, so their melting point will increase. You need more heat for the bonds to break. Their boiling point will increase, same idea, and their densities, being how heavy they are compared to water, will also increase. All right, this is for what? This is for an increase in carbons, whereas branching, it does something different. branching, it will increase what? It will increase the melting point, okay? However, it will decrease the boiling point. So keep in mind, an increase in carbon increases the melting point and boiling point and densities, whereas branching only increases melting point and it decreases the boiling points. Now, let us talk about alkanes reactions. I know this is a long talk about the alkanes, but trust me, everything after alkanes will become much shorter. So alkanes reactions, it has three main reactions. The first reaction is substitution. Okay. Its second reaction is cracking. And its third reaction is combustion. These are the three main reactions of alkanes. In substitution, what happens is that the alkanes will swap their elements with something else, okay? So take the example of CH4, which is methane, in a reaction with Cl2. What would happen is that it would produce CH3Cl and HCl. So as you can see, what happened is that one of the hydrogens from CH4 swapped with what? Swapped with one of the chlorines from Cl2. Now this swap, it is called substitution. Okay? And what is a catalyst for substitution? It is very simply a UV light. Alright, now we will move on to cracking. Cracking is very simply the breaking of long alkanes to shorter ones. So you break long alkanes to shorter ones. Okay? Now, what are the conditions for cracking? We have two conditions. You could sorry, I don't know what's happening. I'm talking so funnily today. You could either use Al2O3 plus SiO2, or, keep in mind, or not and, Cr2O3 in addition, like these are separate, in addition to 500 degrees Celsius, which is mandatory, plus 10 to 12 atmospheric pressure. All right, now this is the process of cracking. Now finally combustion. Combustion, you just need to memorize some formulas. It's the same for everything. For whether it's alkanes, alkenes, alkynes, alcohols, acids, whatever. Any combustion is the same. Combustion in alkanes, it's going to be an alkane. In addition to oxygen, O2, it will produce CO2 plus H2O. This is if we are talking about a complete combustion. If we're talking about an incomplete combustion, it would be an alkane. Plus oxygen, it will form carbon monoxide plus H2O. So keep in mind, these are just the three reactions of alkanes. Now finally, we will move on to alkenes. Alkenes, they are much simpler than the alkanes. So the general formula of alkenes, it is CnH2n. We also know that they are my bad, I think my tablet is glitching because I have 175 pages of chemistry notes. This is probably why it's glitching so much. So it's an unsaturated hydrocarbon. Oh my goodness, you see how much it's glitching? Okay, so alkenes, its general formula is CnH2n. It is an unsaturated hydrocarbon, meaning at least it has to have a double bond or a triple bond. Because it has a double bond or a triple bond, that means it will become very reactive. So it's reactive with hydrocarbons. I'm just gonna write in short hydrocarbons as HC. Okay, and it has a functional group. The functional group of alkenes, it is C double bond C. So whenever you see a C double bond C, you know directly that this is an alkene. Okay, now we will move on to how alkene is prepared. Preparation of alkenes. Now, there's just two ways to prepare alkenes. It is either by the cracking of alkanes. So alkanes, they are long chains. If you crack them, you will at some point form an alkene. Okay? Or the dehydration, meaning the removal of water of alcohols. So whenever you remove water from alcohols, you will get an alkene. Also keep in mind when you're making the isomers of the alkenes, do not form any branches on the terminus, as we discussed above. Directly, without a long process like how alkenes made us go through, we will move on to the alkene reactions. Okay? Now, alkenes have two main reactions. These reactions are either combustion, again, all of them undergo combustion, so I'm just going to put it as an important part, a different part, and addition reactions. Let me start with addition reactions. Let us take any alkene. For example, let us take ethene, which is C2H4. Okay? It will react with Cl2 because it will undergo addition. Look what will happen. Very simply, the ethene, it looks like this. Okay, plus Cl bonded to Cl. What's gonna happen is that this double bond is gonna break and it's gonna form C, H, bond here, H and H. And very simply, because you have two Cl, you're gonna have one chlorine moving to this side and another chlorine moving to the other side. So you will form a new compound, which is whatever this is over here. How do you represent it? This is gonna be very simply C2H4Cl2. So keep this in mind. This is the addition reaction. So just keep in mind that during the addition reaction, the carbon is gonna break its double bond so that the Cl2 or Br2 or whatever can join. Okay, if you want the term definition or the word definition of addition, it is when two or more molecules combine to form one molecule. In this case, we had C2H4 and Cl2. They combine to form C2H4Cl2. Now we'll move on to the combustion of the alkenes. It's very simple again. It's just like alkene plus O2. If it's a complete combustion, it will form CO2 plus H2O. If it is an incomplete combustion, it will be an alkene plus O2. It will form CO plus H2O. Very simply, this is what you need to know. Now, just a little bit more into additions, okay? If you added to it H2, hydrogen, or H2O, gas, steam, or Br2, bromine, or Cl2, chlorine, what would you name this reaction? H2, it is hydrogenation. Okay, H2O, gas, meaning the addition of steam, this is hydration. Br2, meaning the addition of bromine, this is bromination. And Cl2, meaning the addition of chlorine, this is chlorination. Now, what you need to know that bromine by itself, it is a brown substance. So when it will react with an ethene or an alkene, it will form a new compound, and this new compound will cause a decolorization of the bromine or the bromine. because it's forming a new compound. It will no longer be Br2. It will be, for example, C2H4Br2. This new compound will be colorless. Whereas if bromine Br2 was reacting with an alkane, it would just remain brown color. Okay? Now we are going to talk about a different part of addition, which is called polymerization. Polymerization. First of all, what is polymerization? Polymerization is the addition of monomers. So keep in mind, it is the addition of monomers. And what are monomers? Monomers, they are the small molecules to form a polymer. What is a polymer? A polymer, it is a large molecule. So let us take an example. Let us say we have ethene. Ethene, it is C double bond C, H, 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 and H. Let us say we have n number of ethene. The ethene, we will label it like this. You will have n times the number of ethene. If it will undergo polymerization to form a large polymer, okay, so what's happening is you're adding all of these ethenes together to form a large polymer. What's gonna happen is that the double bond is gonna break, okay, and you will have now a bond here and a bond here. So it will become C, single bond C, H, 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 and you will have a bond here and a bond here. But now the difference is that the N will not be next to it, the N will be as a subscript. It will look something like this. This is just the whole idea of polymerization. It is the addition of monomers to form a polymer. Okay, now we move on to alcohols. I believe they will become much easier now. Now, alcohols, their general formula, it is very important to remember their general formula. Okay, alcohols, their general formula, it is CnH to N plus 1 OH. Okay, and they have a functional group which is OH. So OH is their functional group. Now we will move on to the preparation of alcohol. How do we prepare alcohol? We have two ways. The first way, it is called alcoholic or aerobic respiration. Not aerobic, sorry, it's anaerobic. Anaerobic respiration of yeasts. So how does this work? Very simply, it is sugar, for example, glucose, which is C6H12O6, in the presence of yeasts and other conditions. These other conditions are 25 to 35 degrees Celsius, in addition to an airlock system to prevent the oxygen to enter and oxidize the ethanol, or even to give oxygen to the yeast so that they will not perform aerobic respiration. So sugar plus yeasts in 25 to 35 degrees Celsius in an airlock system, it is going to give us an alcohol. So the alcohol in this case will be 2C2H5OH plus 2CO2 plus carbon dioxide. So remember, alcoholic anaerobic respiration, it is C6H12O6 in the presence of yeasts and 25 to 35 degrees Celsius plus an airlock system will form 2C2H5OH, which is the alcohol, plus 2CO2, which is the carbon dioxide. Okay, what you need to know, what is produced is not pure alcohol. Pure alcohol is extracted by fractional distillation. Okay, so what we are forming in alcoholic and anaerobic respiration is not pure, because the yeasts tend to die because of the heat or the amount of alcohol being formed. This is a sad thing, but without it, the alcohol, which can be used as a fuel, not necessarily as the drink alcohol, can be used as a fuel, it could not be formed. So we will write later some uses as of the alcohol. So you do not extract pure alcohol directly. You need to do fractional distillation in order to extract it. Okay, so now we'll move on to the second method. The second method, it is called dehydration of ethene. So all you need to know is that ethene, which is an alkene, if you add to it steam, okay, it is gonna form what? It is gonna form an ethanol. But of course, there are other conditions. What are these other conditions? These other conditions are 300 degrees Celsius and 60 atmospheric pressure and phosphoric acid. Okay, so let us just recap the two ways to prepare alcohol. You can use either alcoholic or anaerobic respiration, which is glucose in the presence of yeast and 25 to 35 degrees Celsius in an airlock system will produce 2C2H5OH plus 2CO2. Pure alcohol is extracted by fractional distillation because, remember, anaerobic respiration will not give us directly pure alcohol. You need to distillate it. The second way is by dehydration of ethene. You take ethene, you add steam to it, it will form ethanol. Of course, you need to add some other conditions, which is 300 degrees Celsius, 60 atmospheres, and phosphoric acid. So I will draw just a little table to compare the two. So here is a small table to compare the two. First thing we're going to be talking about is fermentation. Where does fermentation occur? It usually occurs in a lab. Its resources are renewable, for sure, and its process type. Let us discuss its process type. Its process type is a batch type. That means they do batch by batch, and then after a batch finishes, they have to clean, and then they have to prepare to use a new batch. So it's called a batch process, and it is very inefficient. Okay? Now, the rate of reaction is slow because, of course, yeasts are not going to be very fast in making alcohol. The equipment is small scale, it's not too expensive. The quality, it is an impure ethanol, as we discussed above. You will get an impure ethanol, so you will need to do fractional distillation. What are the conditions needed? The conditions needed is gentle temperature and pressure, so gentle temperature and pressure, and its cost is low compared to the second thing we will discuss, which is the hydration done in industries. So hydration, this is done industrially. Okay, its resources are non-renewable. Okay, its process type is a continuous process, meaning that it will continue going on, and because it will continue going on, it is very efficient. I apologize for my handwriting. I don't know, half of the time my screen is glitching. Its rate of reaction is rapid, meaning it is very, very, very fast. And its equipment, even though they are large, they are also very simple. The quality is pure ethanol. Okay? Its conditions are high temperature and pressure. Okay, and then finally, its cost is high. So this is the table of comparison between fermentation and hydration. Okay, now we will move on to the uses of ethanol. So uses of, not ethanol, uses of alcohol in general. Okay, alcohol, as we said, it can be used as a fuel for cars. It can be also used as a solvent because, as you know, sugar will dissolve in the alcohol. It is also used in beverages, it's like any alcoholic beverages, and it's also used to make raw materials. Okay? Now we will move on to what? We will move on to the reactions of alcohol. So, reactions of alcohol. Alcohol undergoes three main reactions. The first one, of course, it is combustion. The second one is called oxidation. And then the third one, it is called esterification. Esterification. Okay, so first of all, for combustion, as we know, there is incomplete and complete combustion. For the complete, it's going to be an alcohol plus O2. It is going to give us CO2 plus water. If it's incomplete, it's going to be alcohol plus O2. It is going to give us CO plus H2O. Okay? However, when it undergoes oxidation, it's going to form, when alcohol undergoes oxidation, it's going to form a carboxylic acid and water. So the equation for oxidation is alcohol will undergo oxidation. Whenever you see this, that means it undergoes oxidation to form a carboxylic acid, in addition to water, H2O. So reactions of alcohol, we know combustion is alcohol plus O2 will give us CO2 plus H2O. Alcohol plus O2 will give us CO plus H2O. And then finally, alcohol undergoes oxidation. It will be carboxylic acid plus H2O. Now, esterification, which is the final equation, or the final reaction, it is acid plus alcohol. So if an acid will react with an alcohol, it will produce an ester plus water, and the same thing will happen in reverse. Of course, there are the conditions, which is an acid catalyst. This acid could be, for example, H2SO4, HCl, just in general, an acid. So, the reactions of alcohol are combustion, could be a full or partial, or like a complete and incomplete combustion. Oxidation, when alcohol undergoes oxidation, it will be carboxylic acid plus H2O. And then esterification, it will be an acid plus alcohol, and it will form an acid catalyst, an acid plus alcohol in the presence of an acid catalyst. It will form ester and water, and the same will go vice versa. So now we have one of the last, I think it is the last, so the last family or homologous group is carboxylic acids. So carboxylic acids, they undergo the general formula, which is CnH2n plus 1 COOH. So please remember their general formula, CnH2n plus 1 COOH, and their functional group, it is COOH. Now we will discuss the preparation of acids. Preparation, it's glitching, okay. Preparation of acids. So there is only one way to prepare these acids, one way that's given in the notes, and this is the oxidation of alcohols. So very simply, to prepare these carboxylic acids, you only need to oxidize or do the oxidation of alcohol. So now we will move on to the reactions of carboxylic acids. I'll just write over here reactions. Bear with me, my tablet is glitching because of how many papers I have. So we have four main reactions. Okay, let me just fix this a second. Reactions. Okay, these I am gonna list them because I need to write their equations. So the first reaction is the reactions of acid with metal. An acid will react with a metal to form an organic acid salt, to form an organic acid salt plus hydrogen, H2. Okay, now how exactly do we name this organic acid salt? Very simply, it is gonna be the name of the metal plus the prefix of the acid, meaning how many carbons are there in the acid. This is what is meant by the prefix of the acids. Plus, you will end it with ano weight. So for example, if the acid has, let's say it's magnesium, just as an example, the metal is magnesium, it's gonna be magnesium. And let's say you have 2 carbons, let's say, in the acid, so it's gonna be ethanoate. So magnesium ethanoate. Oh, I totally forgot to explain how to name the acids. So let us discover how to name the acids. Very simply, to name the acids, it's gonna be the prefix, which we know the prefix to be how many carbons there are in the acid, in addition to anoic acid. So for example, if we have 1 carbon, it's gonna be methanoic acid. If we have 5 carbons, it's gonna be pentanoic acid. Okay, so we just finished discussing the first reaction, which is the reaction with metals. If then the second reaction is the reaction with metal hydroxides, so it's gonna be acid plus metal hydroxide. It will give us again organic acid salt, but this time it is water, not hydrogen. Okay, so this is another reaction. So again, acid plus metal will give us organic acid salt plus H2 gas. How do we name the organic acid salt? It's gonna be the metal plus the prefix of acid, meaning how many carbon is there in the acid, plus anoate. Second reaction is acid plus methyl hydroxide. It will give us organic acid salt plus H2O, water. And then the third reaction, it is acid plus metal carbonate. Okay, this will also give us organic acid salt, but it will give us water, so plus H2O plus carbon dioxide. Just keep these in mind. Okay, so just a quick recap. 3 of the 4 reactions are acid with a metal. So acid with a metal will produce organic acid salt plus H2 gas. To name the salt, it's metal plus the number of carbons in the acid plus anoate. For example, magnesium ethanoate. Then if an acid reacts with metal hydroxide, it's going to be organic acid salt plus water. And if an acid reacts with a metal carbonate, it's going to be organic salt plus H2O plus CO2. Now, the last process, or the last reaction, which is number 4, it needs a page by itself because it is like a whole explanation of the process. It is called esterification. Do not forget this I over here. It's not esterification, it's esterification. Okay? Very simply, esterification comes from the word ester. And the ester group, it looks something like this. So this over here is what? This is an ester group. The equation we need to memorize is that acid plus alcohol, it will give us ester plus water. Of course, there are some conditions. The conditions, we don't need to know them, but from the acid to the ester, so from acid plus alcohol to ester plus water, the forward reaction, this is esterification, okay? And the backward reaction, meaning ester plus water to acid plus alcohol, this is hydrolysis, okay? Now, very simply, to name the ester, this is very important because they came in the AMS. To name the ester, very simply, I'm gonna zoom in because it will take a lot of space. To name the ester, the first thing we're gonna do is we're gonna use the carbons of the alcohol. Okay, and then in the end, we are gonna add YL. So to name an ester, we are gonna take the carbons of the alcohol. So you will come to the alcohol, you will say, okay, it has 3 alcohols, so it's gonna be prop. So it's gonna be propyl because we're gonna end with YL. If it has, let's say 4, it's gonna be butyl, for example. Yeah? And then you are gonna add it to what? You are gonna add it to the carbons of the acid, okay, plus anoate. So the carbons of the acid, let's say it is, we have 1 carbon in the acid, so it's gonna be methanoate. So if we had 3 carbons in the alcohol and 1 carbon in the acid, then its name would be propyl, okay? Then methanoate. So propyl methanoate. Keep this in mind. Okay? So just a quick recap over esterification. Esterification is based on the ester group. The ester group looks like this. The forward reaction is acid plus alcohol will give ester plus water. This is esterification. Then the backward reaction called hydrolysis, it is ester plus water will give acid plus alcohol. To name an ester, it is the carbons of the alcohol plus yle, in addition to the carbons of acid plus anoate. So now we will move on to fuels. Okay, what do you need to know about fuels? Just you need to know that there are some main fuels. Okay, these main fuels, they are petroleum, okay, natural gas, and coal. Now, what you need to know about each of these 3 is what they are composed of. Okay, before I move on to what they are composed of, you should know that the main fuels, they are all fossil fuels. Okay? So let us move on to what they are composed of. We have petroleum, natural gas, and coal. Petroleum, it is composed of a mixture of many different hydrocarbons. So it's a mixture of hydrocarbon. HC means hydrocarbon. Natural gas, it is 94% methane. Okay? And then finally, coal, it is carbon. So these are just what they are made of. Petroleum is a mixture of hydrocarbons. Natural gas is 94% methane, and coal, it is carbon. Okay? Also keep in mind that fossil fuels are non-renewable. That means that petroleum, natural gas, and coal are non-renewable pollutants. Okay? So because petroleum, okay, or crude oil, another term for petroleum is crude oil, is a mixture of many different hydrocarbons, okay, we will need to separate it into different hydrocarbons so that we will be using it to its full potential. So we have something called petroleum. I don't know if I wrote it correctly. Petroleum or crude oil refining. We have the first process, which is fractional distillation. Then we have the second process, which is purification of the fractions. Okay, so again, keep in mind that petroleum, another term for petroleum is crude oil. It's a mixture of many different hydrocarbons. So for sure, we need to refine it. How do we refine it? We use fractional distillation and purification of the fractions. Now here I am gonna draw something. Okay, so I'm gonna cut off and draw. So over here is what I wanted to draw. This is something very, very important. So as you can see, these are the fractions of crude oil or petroleum. I will write over here, fractions of petroleum. Keep these in mind. Okay, as we move from up to down, okay, the chain length increases. Okay, and as we move from up to down again, let me make it a bit more spacious. From up to down, it will become less volatile. And if we move from up to down, that means that the boiling point increases. And then finally, from moving up to down, the thickness or viscosity will increase. Okay, so as you can see over here, petrol gas is at the top, meaning it has the shortest chain length. It is the most volatile, meaning it evaporates readily. It has the lowest boiling point, okay, and it is very thin, meaning it has a low viscosity. And as we move down, meaning as we move from petrol gas all the way down to bitumen, you will see that bitumen will have the longest chain length. It will be the least volatile, meaning it will not evaporate readily. It will have the highest boiling point, and it will be the thickest, meaning it will have the highest viscosity. So if they ever talk to you about fractional distillation, you should know that it is what? It is the separation due to difference in boiling points or due to the volatility. Okay? Okay, now we are gonna move on to the cracking. Okay? We have two types of cracking. We have thermal cracking. So thermal cracking, you just need to know that its conditions are 700 degrees Celsius and 30 atmospheric pressure. Then we have catalytic cracking. Its conditions are more demanding, meaning it needs 500 degrees Celsius normal atmospheric pressure. However, it needs a mixture of silica or silicon IV oxide and alumina, I believe it's called, or aluminum oxide. So you could just say silicon oxide, silicon IV oxide, and aluminum oxide. These are just some extra information. Sorry, my tablet keeps on glitching. I have almost 200 papers. Okay, and now we move on to the last topic. We finally reached the end of chapter 5, so it is called polymerization. What about polymerization or macromolecules? We have two types of polymerization. We have either addition polymerization or condensation. Okay, now what is the difference between addition and condensation? Okay, I wish my handwriting could be better, but my tablet is lagging so much, I apologize. So addition, it is a single product, whereas in condensation it is the removal of H2 or H2O in joining process. Okay. That means in the addition process, a single product will be formed, whereas in the condensation, it is the joining of these monomers, but during the joining process, there is a removal of H2 or H2O. Usually, the monomers in addition, they are unsaturated. Okay, so unsaturated like what? Like the alkanes or alkynes. And to undergo the addition process, they will break the double. It will break the double bonds. Okay, whereas all you need to know about condensation is that it's the removal of H2 or H2O in joining process, and it has two functional, oh my goodness, two functional groups. Okay, so what you need to know in polymerization, we have two different types, addition and condensation. Addition will give you a single product. This single product is due to the result of the addition of many monomers that are unsaturated. And how do they become polymers? By the breaking of double bonds. Whereas in condensation, you're adding the monomers together, but you're joining them together, but there will be a removal of H2 or H2O, and it has two functional groups in this process. Now we will go to the synthetic and the natural polymers. All you need to know about the synthetic polymers is that in condensation, we have two main synthetic, and these are polyesters. So they are polyesters or polyesters, however you want to say it, and polyamides. These are the two main ones in condensation. In addition, they are anything that you see poly. Addition, it's gonna be poly plus whatever. Anything that you see poly in the addition process, then you know that it is a synthetic polymer. Whereas for the natural polymers, we have proteins, DNA, cellulose, silk, wool, and rubber. I think my notes are so full to the point that no, it will not work anymore. So just like a quick recap of polymerization, we have two types of polymerization, which is addition and condensation. Addition will form a single product and its monomers are unsaturated. That means you have to break double bonds to join them. And in condensation, you're joining the monomers together, but throughout the process, there will be the removal of H2 or H2O, and it has two functional groups. We have different types of polymers. They are synthetic and natural. For the synthetic, it's anything that has poly in front of it, whereas for the natural, we have proteins, DNA, cellulose, silk, wool, and rubber. Thank you guys for watching. I hope you enjoyed this very long video about chapter 5. Chapter 5, let me find where I actually wrote it. Chapter 5, here we go. Chapter 5, Organic Chemistry, which is almost 32 pages long. I hope you guys understood, and if you have any questions, yes, of course, you can comment.